which they were kind enough to clean the blackboard once a year. They did it with all the material on the blackboard. I guess it's a good thing. The blackboard's nice. Are there any questions? Okay, so are we ready? Okay, thanks. What we were looking at was, in the last class, we started looking at canonical systems. By canonical systems, we just mean systems that we come across very often in mathematics, but in every situation the notation is a little different, but the mathematics is the same. So what we do is we take some sort of notation that is not problem specific, so that rather than calling a concentration and a flow rate, we just say a dependent variable and an independent variable, so etc. And that way, whatever situation we come up with, whether it's temperatures or concentrations, if they give me the same equations, I just always put it in the same form. So we had looked at non-interacting systems. And those were systems, for example, in series, where we had like first-order systems in series. The prime example was CSTRs in series, where the information flowed in one direction. That is, tank 2 only depended on tank 1 and what was going into tank 1, but not on tank 3. Tank 3 only depended on 2, 1 and what was going into 1, not on tank 4. And we saw that that situation was very simple in the sense that as the result was very simple and intuitive. Are you able to record? It's very simple and intuitive because what we found was that the G tilde, the G tildes for the entire system was just the product of the individual G tildes of the individual systems. So therefore, the time constants, that is, remember the time constants for first-order systems were the things that went into the exponentials, which told us how things decayed. The time constants for the non-interacting system was just the set of time constants of the individual systems. So there were no surprises in that situation. Moreover, the steady-state gain of the overall system was just the product of the steady-state gains of the individual systems. So it was really, that was kind of nice because there was no surprises. Okay, and then what we said is, okay, let's move on to the more complicated case, or the one that might be a little less intuitive, is the interacting system. As you notice, so here, again, the interacting system, it could be, there are many different physical situations that lead to the same equations. The whole point is that now system 2 doesn't just depend on system 1 and what comes into system 1, but it also depends on system 3, system 4. So all the systems depend on all the other systems. And let's see how that one works. And one example we gave here was where we had a bunch of tanks all connected with a big pipe. This is one of many system situations that could work this way. We could also have CSTRs separated by membranes where I have diffusion going back and forth between through the membranes that are allowing the species to diffuse between. There are many other situations. And here I have the input x prime, and here I have the various heights. And we look at the flow between tanks just by hydrostatics. So if there's a difference in height, if this is higher than this, then there's a net, then this height from hydrostatics, if I have pressure is the atmospheric up here, above all the tanks, and they're all exposed to the atmosphere, then from hydrostatics there's a net flow in this direction, rho g times delta y, and I just lump those rho g's into these k's. So k1 is for the difference between, is what moves you from tank 1 to tank 2, or vice versa. K2 is between tank 2 and tank 3, etc. And I can have many of these. Okay, so what we did is we started by writing the boundaries for tank 1. This is tank 1. And we say the change in volume of tank 1 is equal to the flow rate A. So x prime is units of flow rate here. So this is y has units of height, time, area. So this is volume versus time. So this is And then minus k1, y1 minus y2. Obviously, if y1 is bigger than y2, the flow is this way. If y2 is bigger than y1, the flow is the other way. If y1 is bigger than y2, it depletes tank 1. That's why I have the minus sign. And then I just rearranged. I noted time constants are typically area divided by A, gave me a time constant. So I divided through by K1, and that gave me a T1 here. And I moved this to the other side of the equation, so I got the plus y1. And on the right, I still had the x prime over K1 minus and minus K1 y2. That's why I got the plus here. And again, the K1 down here is because I divided by K1 to get the time constant. Then when I Laplace transform, I get 1 plus ST1 on the left onto y1 prime tilde. And these things just became tildes. And I divided by 1 plus ST1. And I noted that G for x prime tilde influencing y1 prime tilde is y1 prime tilde over x prime tilde. So it's 1 over K1 times 1 over 1 plus ST1. And the G for how y2 prime tilde influences y1 prime tilde is y1 prime tilde over y2 prime tilde is just 1 over 1 plus ST1. So I did that algebra at the end of the last hour. And then I moved on, and this is exactly how far I got last hour. I said, I may have done one more line. I'll get to that now. Here I do the balance on tank Y2, and Y2 has fluid exchange with tank 1, depending on which one's higher, and fluid exchange with tank 3, depending on which one is higher. And then all I do is I move all the Y2 factors to the other side of the equation and divide by K2. When I divide by K2, I get a T2. When I divide this by K2, I just get a 1 coefficient, and here I get a K1 over K2 coefficient. And what's left on the other side is K1 Y1 prime and K2 Y3 prime. So now what we said we're going to do is we're going to Laplace transform. When we Laplace transform this, we get Y2 prime tilde. And here I have a 1 plus K1 over K2 plus ST2. So this is going to be 1 over 1 plus K1 over K2 plus ST2. Because that was the coefficient here. Times K1 Y1 prime tilde plus K2 Y3 prime tilde. And of course I have the K's not right. I divided through okay, I think I did the algebra a little too quickly. So let's just check the algebra here. I divided through by K2, that gave me a T2. I got K1 over K2. I got a 1. And this one was the thing was K1 over K2, and there's no K2 here. Because I divided through by K2. So here I have a K1 over K2, and here I have just a 1. I just got to fix that little algebra, because at this point I divided through by K2. And it just as here, I divided by K1. Okay, so I think this is where I was last time. I may have gotten this last equation. And the idea here is, I would like to, when I have a series, if you remember, when I had a series of CSTRs, I didn't want to have all the intermediate concentrations. What I wanted to do is I wanted to have everything in terms of the beginning, the first one and the last one, nothing else. So if you think of Y3 as the last one, and X prime is what's coming into the first one, I'd like to get Y2 in terms of Y3 and X. So I don't want to have this Y1 sticking around here. Obviously, if I had 10 of them, then I would want it in terms of Y10 and X. But that's even more algebra, which I'm not going to do. You get the basic idea from this one. So the idea here is I'm going to plug in for Y1 prime tilde from here, and that will get rid of the Y1 in terms of X prime and Y. And then I'll have a Y on the right and the left, so I'll solve for Y prime tilde. That's the basic idea. And why am I doing this? Remember, I'm doing this because I would like to know the g's. And in particular, I would like to know how changes in the input affect y2, and how changes in y3 at the other end affect y2. Because again, in an interacting system, everything interacts with everything else. So it's not just the stuff to the left, but it's also the stuff to the right that interacts. Again, if you miss anything, or if you're not following, stop me and just ask. Okay. So here I have y2 prime tilde, which is 1 over 1 plus k1 over k2 plus st2. And let's hope I don't make a mistake in algebra. That would be unfortunate. Notice, okay, so now where I see a y1 prime, well, let me just copy this term over because that's easy. Y3 prime. And now I have a 1 over k2, y1 prime. So for y1 prime, notice I'm going to have a 1 plus st1 out here. So I'm going to divide the whole thing by 1 plus 1 plus st1. And if I'm going to divide by that, and this has just 1, I'm going to have to multiply this by 1 plus st1. That way, when I multiply these two out together, I just get the y3 prime. And you'll see that ends up being a little bit convenient. And now let's plug in. I have y2. I have k1 over k2 times y2 prime plus k1 over k2 over k1. That's just x prime tilde over k2. And now what I'd like to do is I would like to move this to the other side, factor it out, and solve for y2 prime tilde. So I have y2 prime tilde is equal. So I have this whole denominator here. Or maybe I should not do too many steps at once. So here I have 1, and now I subtract off k1 over k2, divided by this denominator. 1 plus k1 over k2 plus st2 times 1 plus st1. So that's this term moved to the other side of the equation. It's equal to y3 prime tilde times 1 plus st1 plus x prime tilde over k2 divided by the same denominator. 1 plus k1 over k2 plus st2, 1 plus st1. So it's clear what I did there? I just took this term, which has two factors in the denominator, and I subtracted it from both sides. So that's how I got this. And now I'm going to bring this all under one denominator. That is, I have 1 minus that. And then I'll divide by 2 prime tilde. And that gets, I have to take this whole thing, multiply it, divide the whole thing by this denominator. And that's equal to y3 prime tilde 1 plus st1 plus x prime tilde over k2 over the same denominator. But I have to put it all into the numerator. Again, you don't have to worry about copying down every equation because you can get a picture of this. It's more important for you to see what I'm doing, and you'll get a picture. And my handwriting, unfortunately, doesn't get any better on the photo. So let's multiply this out and subtract k1 over k2. Well, I can notice that this is 1 plus st. Well, let's just multiply it out. Give myself a little more room. Okay, so I notice I'm going to subtract out k1 over k2. So since I'm going to subtract out k1 over k2, this times this guy is going to be separate. So let's take 1 plus st1, st2, times 1 plus st1. So that's this times this. That stays. And then I also have plus k1 over k2 times 1 plus k1 over k2 times st1. But the k1 over k2 times 1 subtracts this k1 over k2. And now you can notice that I have this thing equals this thing. And since they both have the same denominator, I'm going to cancel the denominator on both sides so that I don't have to do that copy over that algebra. The more things I copy over, the more likely it is I'm going to make a mistake. So we have y2 prime is equal to y3 prime times 1 plus st1 plus x prime tilde over k2 divided by a denominator. Then let's multiply all this out. So this is s squared t1 t2. And now I also have s times t2 plus s times t1 plus this. So I've got t1 plus t2 plus k1 over k2 t1. Yes. Plus 1. Plus 1 times 1. So there's y2 prime tilde. And let's just notice that g tilde, this transfer function, remember the g's of the transfer function, for how x prime influences y2 prime. And that again is y2 prime tilde over x prime tilde. That's equal to 1 over k2 divided by this denominator, 1 plus s, 1 plus t1 plus t2 plus k1 over k2 t1 plus t1 t2 s squared. And g tilde for how y3 prime tilde influences y2 prime tilde, which is defined as y2 prime tilde over y3 prime tilde is equal to 1 plus st1 divided by t1 t2 s squared plus t1 plus t2 plus k1 over k2 t1 s plus 1. And again, the point here is that in the interacting systems, it's not just that y1 influences y2, but y3 influences y2. And that's why you see that going on here. And as we started to see the class before last, these g's are they become boxes when we do block diagrams. So that's one reason they're nice, because they become boxes. And probably what I'm going to do, we'll see, I'm leaning towards doing one class while I'm away next Wednesday at the conference by Zoom. And that one, I think what I'll probably do is I'm going to teach you a class that will be on the computer anyway. So there's a program called Simulate, which is part of MATLAB, which you should all have. We have a site license, so if you don't have it on your computer, just ask Andy, and he can put it on, get you the license, put it on your computer. And basically, once you know how to make block diagrams, which we started doing, and you put these g tildes inside each box, assuming you do it correctly, it then does the inversion for you and will make all the graphs. So that's kind of a useful thing to do. It kind of does a lot of the algebra for you. But anyway, let me continue here. Are there any questions so far about what we've done?
Let's say we had 10 tanks instead of 3, right? And you're still interested in tank number 2. Would you consider, obviously, the input
That's a very good question. All other tanks influence it, but the beautiful thing about linear equations, or equations that we've linearized, is that even though tanks 3, 4, 5, 6, 7, 8, 9, and 10 all influence tank 2, I can, by algebra, eliminate tank 2, tank 3, 4, 5, 6, 7, 8, 9, and write everything in terms of tank 10. Which is exactly what I've done. What I'm doing here is I've eliminated tank 2 in terms of tank 3, and that's only because it's linear. And if you remember, even with CSTRs in series, that was also linear, but that was non-interacting. When we had CSTRs in series, we could write the output of tank 10 solely in terms of the input to tank 1 and the time constants. I didn't need to know the concentration of C5. I can eliminate that from the algebra. And the only reason I can do that is, the only time I can do that is for linear systems. But since this is an undergraduate class, it's linear undergraduate. Graduate classes won't be so linear. Are there other questions? Okay, so remember, do we calculate the G's just for fun? Well, not really. We want to know the stability. Because, as you know, for example, if I want to know y2 prime tilde, that's equal to the G times x1 prime tilde. If I want to know y2 prime tilde in terms of y3 prime tilde, y2 prime tilde is the G times y3 prime tilde. So, for example, if x prime tilde, I'm going to 1 here, x prime tilde is a step function, then we know that the Laplace transform of a step function, x prime tilde, is just delta x over s, 1 over s. So the denominator that's going to tell me everything about the dynamics, the denominator that's going to tell me the stability, it's going to tell me, well, the main thing is going to tell me the stability, and G tilde will tell me everything about the response to a sine function. But as far as stability, I only have to look at the zeros of the denominator. So obviously, if I have a step function in x prime, I have that step function, then I'm going to be multiplying by 1 over s, and that is obviously 0 when s is 0. 1 over s is tautology. 1 over s is infinity when s is 0. So, and what does that say? Remember, when there's a 0, that tells me that at least that contribution is just a constant. When I do the inversion, and I invert the 1 over s part, I'm going to get a constant, because I'm going to get e to the 0t. So that term is going to be a constant, which is more or less telling me that if everything is stable, then step function in the input will lead to a finite difference at steady state in the output. Makes sense. If I increase the flow rate, I'm going to increase something at steady state in the output. So let's look at the denominator here, which will tell me if things are steady. So let's look at the zeros of the denominator. So if I want to look at the zeros of the denominator, this is a quadratic equation. So if I look at I'm going to look at the roots of the quadratic, s star. And can someone help me with the quadratic formula? Do we have a volunteer here who remembers quadratic formula?
Yeah,
you have to take your math now.
So in terms of that equation, it will be negative t1 plus t2 plus k1 over k2 t1 plus or minus the square root of that same term squared.
Right, I can't write that fast.
Oh, sorry.
I know I write fast, but not that fast. Okay.
And then minus 4, and then the a term is going to be t1 times t2, right? And then, yeah, there you go. And then it's just all over 2. Because
over 2a.
Over 2a, I'm sorry, yeah.
Okay, so thank you. And now let's multiply this out for a second. First of all, let's notice that the magnitude of the thing of the square root is less than the magnitude of this, because it's this thing squared minus something that's positive. So if this thing is, if the discriminant is positive, its square root will be real, but it will be smaller in magnitude than this. So even if I add it, the answer will still be negative. So if